Okay, here we are, question 9b, part B. All right, so now so we're going to show that the particles A and B will collide. Okay, so if they collide, they must be in the same place at the same time. So that means that vector R and vector S must be equal, and not only must they be equal, but the time must be the same when they're equal. It's a bit vague. So collision is different paths crossing. So, paths cross, they could be go through the same position, but at different times. So with the collide, they've got to go through the same position at the same time, and then therefore they would then collide. All right, now this is another one where there's a bit of working and not much space, so I'm actually going to divide this into 3. Because the easiest way for me to look at this is to look at I components and J components of each of these two particles. So if they've got to be in the same position at the same time, then their I component for each of them's got to be the same, and the J component's got to be the same. So that's back up here at the top, and here's our equation. So the I components have got to equal, and the J components have got to equal. All right, so transcribing those back down here, then for the I components, -1 plus 4 cos t has got to equal 3 sec t minus 1. All right, so if we then add 1 to both sides there, you've got 4 cos t is equal to 3 sec t. All right. Now, sec, of course, is 1 on cos. So if I've got 4 cos t then equals 3 on cos t. And if I do some rearranging, times both sides by cos t, so you get cos squared t, equals, and divide both sides by 4, equals 3/4. And so then if I square root that, cos t could be plus or minus √3 on 4. All right, so there's the I components. And so we know that cos t could be plus or minus √3 on 4. All right, for our J components, 2 on √3 sine t has got to equal tan t. All right, and I think that's right. Yes, that is right. If I now move the tan over, 2 on √3 sine t minus tan t equals 0. Now, the reason that I've done that is because tan is sine t on cos t. So what I'm going to do is I'm going to create a common denominator. So I'll have 2 sine t cos t here over cos t. And the reason that I have done that is that now up the top here, when I put these together, we've got sine t is a common factor. So sine t outside of 2 cos t minus 1 all on cos t equals 0. So what does that mean? Well, if that's going to equal 0, the numerator's the bit that we're interested in. So sine t could be equal to 0. Oops, I've lost my root 3. Sorry, on root 3 here. And I need to, when I create my common denominator, it's not just going to be cos t, it's going to be root 3 cos t. So I need a root 3 here, root 3 here. So it's not minus 1, it's minus root 3. All right, and that's where these 1 mark show questions are tricky. All right, because that one error there would mean I've got no marks for all of this. All right, so 2 cos t minus root 3 equals 0. So we'll have either sine t equals 0, and if I rearrange that, add root 3 to both sides, and I notice I made another mistake, error, and I'll get to that in a minute. Add root 3 to both sides and divide by 2, I get that cos t equals root 3 on 2. Now, the other error I made was over here when I square rooted. I forgot to square root the 4. All right. So again, as I said, these are tricky. So that's on 2. All right. Okay, so here we've got a cos t and a sine t and a cos t here. And so now what we've got to do is we've got to have a look, because they have to be at the same place at the same time. Now, when you look at this here, cos t could be plus or minus root 3. And when you look at the j component, cos t is root 3 on 2. So that's positive root 3 on 2. So for the I and the j components, cos t equals root 3 on 2 is common. And so that means that the particles collide. All right, because when cos t is positive root 3 on 2, these two particles, A and B, will be at the same place. All right, depending on their motion, they may be at that place at other times, but the key thing here is plus root 3 on 2. They're in the same x and the same y when cos t is root 3 on 2. All right, and so that's where the examiner's report left it. They didn't work that out, but just as a side, if you did work that out, you'll find that t is pi on 6 for that. All right, now it says, hence find the coordinates. So I'm going to find the coordinates of the point of collision of the two particles. All right, so that's the x and the y values. All right, and so what we can do is use a number of different things to find those x and y values. But what I'm going to do is I'm going to use particle A. We don't have to use both particles. The x and the y values for particle A will be this here. So that's where this t of pi on 6 comes in handy, because my x value of the point of collision is minus 1 plus 4 cos, in this case pi on 6. And the y value is 2 on root 3 sine. And again, it's pi on 6. All right. So what do we know? We know then that's -1. Now, cos pi on 6, we've worked that out. That's the positive root 3 on 2. 2 there, cancels there. 2 on root 3. Sine of pi on 6 is a half. Cancels there. And so the point that we're looking for is -1 plus 2 root 3 and 1 on root 3. All right, so in the examiner's report, they leave that as 1 on root 3. They haven't rationalised the denominator, which is what I would have gone ahead and done. So that suggests in this case you didn't need to do that, but if you had rationalised that, it's root 3 on 3, multiplied top and bottom by root 3. All right, so there's part B. And as I mentioned, you've got to be careful that you don't make some errors like I did make a couple of those slide errors because they're only 1 mark.